Hello, everyone. Good afternoon, and thanks for attending today's webcast. This is session 5B, Multifamily Case Studies and Design. I'm Ben Larson with Larson Energy Research, and I'll be moderating the session. We'll start the webcast with a few housekeeping announcements and then move on to our presentations. So we'd first like to thank all of our sponsors and the ACEEE ally members for their support of the Hot Water Forum and ACEEE. Couldn't do this without them. Next up, please use the chat box on the right-hand side of your screen to ask questions of the presenters. The presenters will not be able to respond to your questions in the chat, but as moderator, I'll gather all the questions and share for the presenters to answer once all the presentations are complete. If we don't get to your question, please join us for 20 minutes of Q&A on the Zoom platform immediately following the session. The Zoom link is posted on the audience screen at the very bottom. And also, when you're joining that Zoom session, you'll also be asked for a password, which is provided next to that link. Also, throughout the conference, be sure to check out all the tabs on the left-hand side of the Socio app. From there, you can network with attendees and program participants, visit sponsor pages, and engage in our game to possibly win a free registration for the 2023 Hot Water Forum in Mission Hills, California. The resources section includes the program and a list of attendees for downloading. And last, we also ask everyone to please help in our planning for future Hot Water Forums by completing the conference evaluation. Anyone who completes the eval and includes a testimonial will receive a $25 discount off the 2023 forum registration. All these presentations will be available for on-demand viewing to registered attendees on the Socio platform within a few days, and that will remain available for viewing until May. Presented slides can be found on their page in the program participants section. So now I would like to introduce our distinguished panel of speakers. They are James Haley, professional engineer with Frontier Energy, Peter Grant with Lawrence Berkeley National Lab, Jonathan Heller, president of Ecotope, and Nick Young, associate director of projects with the Association for Energy Affordability. We're in for a treat today. All four of these speakers have incredible depth and experience in water heating, from research to design to implementation. These guys are truly pioneers in the field of multifamily heat pump water heating. So we're looking forward to their talks. There's three presentations lined up, and they explore the state of the market transformation towards heat pump water heaters in multifamily. Two of the presentations focus on case studies highlighting learnings and pain points, because certainly the pain points is where we get the most learnings. And then one of our presentations is taking a broader view and looking at the state of the market as a whole. So without further ado, we'll start with our first speakers, James and Peter. Take it away, guys.
Cool.
All right, you guys can see our slides, right?
Yep. At least I can.
Great, take it away, James.
Cool. So I'm James Hale, and today Peter Grant and I are going to talk to you about a project that we worked on with heat pump water heaters in a clustered configuration for a multifamily building. Next slide. The project was funded by PG&E under their Code Readiness Program with assistance from 2050 Partners. Neighborhood Partners was the site developer and the building owner. Next. Prior PG&E Z&E design optimization support led to this project, which presented an opportunity to gather high-resolution field data for 10 heat pump water heaters over 18 months in a multifamily building in a central configuration. We wanted to look at load shifting as well and compare that to the fixed set point operation. The load shifting being where we maximize the use of the midday PV and minimize on-peak energy usage. We wanted to make sure also that we were actually providing effective load shifting, not just providing well-timed demand response. So we wanted to make sure that we were minimizing electric resistance heat use during the load-up period. All of the data collection and analysis for this fed into a detailed simulation model, which Peter will talk about in a bit. and the model will be publicly available following the project completion. And we used it to develop, to evaluate performance, cost, and other metrics for different control strategies and sizing. Next. Our test site was the Creekside all-electric Z&E affordable multifamily project. This is a 90-unit low-income and special needs housing project in Davis, California, with 40% of the units being prioritized for the disabled and homeless. This makes the data that was collected for this project very interesting from a demographics perspective, as these are groups that may be underrepresented in your typical usage study. Next. Also the fact that this is low income and special needs housing brought a lot of focus on the centralized or clustered heat pump water heater design and its costs. At Creekside, rather than having individual heat pump water heaters per unit or a large central system, we had clusters of 4 apartments per heat pump water heater. The heat pump water heaters themselves were installed in exterior closets. And well, the disadvantages of this configuration are all things that you would expect, such as increased hot water runouts due to higher loads per water heater. The configuration had a big advantage in reduced first costs relative to other options, including central gas. This is, of course, important for affordable multifamily housing, but it's very important for multifamily in general and for heat pump technology adoption, as first costs are often the only things that builders are concerned about. Next. This is the heat pump water heater that we used. It's a very basic 80-gallon unitary heat pump water heater with a tiny compressor and about 4.5 kW of backup heat. It's basically exactly what you would think of when someone says unitary heat pump water heater. This is what it looked like installed in the exterior cabinet sans plumbing insulation. The astute members of the audience will probably immediately notice a potential issue that we'll get into in a couple of slides. But that's basically what it looked like. Next slide. The heat pump water heaters were monitored using BTU meters to monitor the hot water demand and a true RMS energy meter to monitor the electricity use. These devices calculated energy rates and totals many times per second, and both rates and totals were logged at 15-second intervals. Because we were doing load shifting, we needed to have a mixing valve so we didn't send scalding water to the fixtures, and because we really wanted the actual hot water draw data, not just the amount of hot water coming out of the tank, we put our BTU meter on the supply side of the mixing valve. We also logged ambient conditions in the cabinet at 1-minute intervals, with the sensor placed so that it could effectively capture the inlet air temperature of the evaporator. We also monitored the outdoor weather conditions from a nearby weather station that we controlled so that we could control the logging rate. All of this was uploaded every hour from all 10 closets via cell modems to our monitoring server, which also performed an automated daily performance analysis. Next. So cool stuff for collecting interesting data. The cell modems, oops, back one. Sorry, Peter.
It's all good.
The cell modems also provided the heat pump water heaters with an internet connection, which we used to control the heat pump water heaters through the manufacturer's cloud API. This also got us some additional data, such as the upper and lower tank temperatures, though the water heater would only push new readings to the cloud when there was a significant change in the reading instead of at a regular interval. And that was never defined to us, but it was still good to have. Controlling the heat pump water heaters through the API proved to be quite the challenge. We encountered several issues along the way. The greatest challenge that still persists in the current implementation of the API is that the API does not verify that the target heat pump water heater received and implemented a command, and it does not repeat commands ever. So often we would schedule a load shifting event and then sit back and watch as it didn't happen. Or the load up set point would be sent, but not the peak period set point. So the heat pump water heater would merrily maintain a 140-degree set point for 8 hours or more, and sometimes straight on into the next load up period. All of the issues that we encountered with the API, including some concerning security holes, are documented in our report. And like many other things that we encountered in the course of this project, could be a 20-minute presentation unto itself. Next. One of the other things that there's been a lot of interest in from this project have been the airflow issues that we encountered with the heat pump water heaters in the small cabinet. You may have noticed back on slide 6 that the air exhaust was not pointed directly at the louvered door. But this was in keeping with the diagram and the instructions in the installation manual that shipped with the units, at least as far as how both the designer and the installer interpreted them. So if that was not the correct interpretation, knowledgeable people looked at it and came to the same conclusion. Another thing worth noting is that if the tank were pointed so that the exhaust was pointed directly at the door, the screen would be very difficult to see and access, and the plumbing connections would be almost completely inaccessible. The instructions do note, though, that if the ambient temperature in the cabinet drops 15 degrees during heating, then the air circulation is insufficient and the unit must be ducted. We noted typically a 20-degree drop in the first half hour of the heating cycle during our post-commissioning period, but before occupancy, which is clearly, much more of a drop than that criteria. Now, obviously, switching from unducted to ducted is very difficult when you've already finished the building. You designed around a non-ducted configuration. People are moving in. There are massive headers over the doors, so you can't duct over the door. There are bedrooms on either side, and nobody wants a heat pump water heater duct going through their bedroom. So we ended up ducting through the door. We tried out a couple of different methods, but ultimately went with flex duct and a boot that went through the door. It is a imperfect solution because it was still, it was a little restrictive and it wasn't insulated, but it still reduced energy use by 14% over the unducted configuration. And it ensured that the data that we collected would be representative enough for use in our analysis and modeling, which Peter will get into now.
Yeah, so as James has said a couple of times, we ended up creating a new simulation model for this project, with a lot of the motivation there being that we needed something that's flexible enough to both accept the Creekside monitored data and to accept simulation assumptions. So we created the flexible heat pump water heater performance predictor, which I typically just refer to as Flexi. And this is a simulation model that has all of the typical standard features of a heat pump water heater simulation model, plus an easily edited external configuration file, so that as you do more simulations, looking at products from more manufacturers, or maybe change the compressor size to try a theoretical different design, you can just create this library of different models that you can use at any time you please. To further improve the flexibility of the model, we created a number of different supporting libraries that you can use to just overwrite different parts of your data to create different simulations. For instance, depending on what climate zone in California you want to simulate, you can just call a function that overwrites your air and inlet water temperature data with simulation assumptions for those zones. And we could do climate zones in other parts of the country as well. We just haven't added that capability yet. We can do the same thing with set temperature profiles. So if you want to look at different static set temperatures or different dynamic load shifting set temperatures, control strategies, you can just call the right function. And again, it will overwrite whatever data you have with the right set temperature profiles for that simulation. We also set up a library of different installation options. So you can look at how this heat pump water heater will perform when it's installed in different locations. So you could do a simulation with it in the garage versus simulation with it in the small closet with constrained airflow like was originally at Creekside. Or you could look at it in that same closet with ducted exhaust like is now installed at Creekside. And Flexi has been validated against the Creekside data and shows errors within 5 or 10% on several key performance metrics. but it's not perfect. And so I have a few plots here showing the strengths and weaknesses of it. The plot on the left shows 7 days of operation during April of 2021, when the simulation model performed very well. Over that week, there's less than 1% error, and there's a very close match on timing when you compare the simulation model to the monitored data. This is especially true on April 14th, where you can see that the unit started using the heat pump to heat the water, realized it couldn't keep up, and switched over to second stage heating, which did eventually bring it up to the set temperature, and the unit shut off. And in this case, Flexi got both the heat pump and the electric resistance elements nearly perfect in terms of both electricity consumption and timing. So that was very good. But then there are other control modes that we don't understand in these heat pump water heaters. Specifically, we know that they have a safety shutoff when the air temperature is below 37 degrees, and they will switch to electric resistance only mode to avoid damaging the heat pump. But you can see in the plot that I have on the right, it went into electric resistance only mode when the air temperature was between 49 and 57 degrees Fahrenheit. So clearly it's not that control mode. We believe it's a secondary safety mode that it uses when the water temperature in the bottom of the tank is cold and risks damaging the heat pump, but we don't have the data to verify that claim, so we're not sure, and we haven't programmed that into the simulation model yet. Now, we used Flexi to do a parametric study looking at the annual impacts of several different control strategy and design changes when using the Creekside data sets. So we looked at different fixed set point and load shifting control strategies. And then we also looked at different system designs. 4 system designs that we're highlighting here are what happens when you have that same 80-gallon heat pump water heater serving 4 apartments, versus what happens when you have that 80-gallon heat pump water heater with a 1-ton compressor serving 4 apartments. Or what if you have that 80-gallon heat pump water heater serving 3 apartments? Or what if each apartment has their own separate 50-gallon heat pump water heater? And we looked at all of these different cases with 3 monitored input data sets. We chose 3 of the heat pump water heater profiles from the monitored data, one representing a low use case, one representing a medium use case, and a third representing a high use case. So we're both bounding the problem and looking at the average situation. And then when we were running these simulations, we also used the monitored air and water temperature data from the Creekside project. So these are all cases of things that happened in real buildings, and it's real data driving the simulation model, but it is a kind of targeted case. And so here I have some sample simulation results over the next couple of slides. With this slide looking at the electricity cost and peak period electricity consumption with those 4 different system designs that I talked about previously. And you can see that when we switch from each apartment having their own heat pump water heater to the shared configuration with 4 apartments sharing an 80-gallon heat pump water heater, the annual electricity cost drops substantially. And this is because of jacket losses. Now you have 1 heat pump water heater instead of 4, so there's less jacket losses and simply less load. But it doesn't perform as well in terms of load shifting performance, and there is more electricity consumption during the peak period when using the shared configuration. And this, of course, is because it's shared. Now you have 20 gallons of storage per apartment instead of 50, and you have 1/4 as much heating power per apartment. So the heat pump water heater simply can't perform as well during the load up period, and it simply has less storage per apartment to coast through the peak period. And then, as I'm sure will surprise nobody, when we use that same shared configuration with a 1-ton compressor, you have lower electricity cost and lower peak period electricity consumption. And this is just because, the bigger compressor can keep up with the load better. It doesn't have to use the electric resistance elements as much, and it does a better job of loading up before the peak period. And we're running a little bit late, so I'll skip over the 3 apartment case, but you can see there were savings there as well. Then when we look specifically at peak period electricity consumption, we can see that, again, there's a benefit from switching from individual heat pump water heaters to the shared configuration, which is again driven by jacket losses. There are lower jacket losses, so there's less heating required. Then when we start implementing the load shifting controls in the shared configuration, we see a 65 to 81% reduction in peak period electricity consumption. And this is what you would expect. You heat up the tank higher before the peak period starts. You don't need to heat as much during the peak period. But when we look at cost and CO2, the results aren't quite as straightforward. We still see a big improvement switching from individual heat pump water heaters to the shared configuration. But when we start implementing load shifting in the shared configuration, we actually see cost and carbon dioxide emissions increase. So what happened? Well, the problem is that these units, since they're shared between 4 apartments, already have high loading. And the heat pump is already struggling to keep up with the load. And then when we start increasing the set temperature, we're also increasing expectations at the same time that they're struggling. So the heat pump can't keep up, and it switches to using the electric resistance elements more often. So yes, we are paying less money per kilowatt hour. And yes, we are emitting less carbon per kilowatt hour. But since we're consuming significantly more kilowatt hours, that, overrides all of the benefits. That said, when you look at the actual numbers, switching from individual heat pump water heaters to the shared configuration reduces cost by 25% and carbon by 17%. And then implementing load shifting was still improving cost or decreasing cost by 20% and decreasing carbon emissions by 11%. So there are still benefits here. And there are especially benefits when you do the comparison between the shared system and the individual system without load shifting. Some of the advantages are that you simply pay less per apartment to install it. And since you consume less electricity per apartment, you also pay less on annual operating costs. And since you're consuming less electricity per apartment, there are also carbon emission reductions. And this is only looking at the operating carbon emission and not taking into account refrigerant leakage. So when you take into account that you have 1 heat pump water heater to risk leakage instead of 4, that's going to get even better. But there are cons to this approach as well. As James mentioned, there's more loading on each heat pump water heater, so you're going to have more runouts. And in our most highly loaded unit, 9.4% of all delivered hot water was too cold and considered part of a runout event. So these systems clearly need to be designed well. Also, since these units are more heavily loaded, you can't perform load shifting as well, and you're going to end up with more peak period electricity consumption. Now, there are several projects we need to continue as we continue this work. Specifically, we need to do detailed lab testing so we can evaluate this system in a very controlled environment. And we need to look at different manufacturers, different communications protocols, and different installation configurations so we can really understand how this works. Then we need to use that information to develop a Title 24 compliance option so that builders who want to use this system and do a good job can get the credit they deserve. Also, since we started this project, CTA 2045 has included an advanced load up feature. And this advanced load up command enables you to set a preference for using the heat pump instead of the electric resistance element. So that could solve the issues that we were seeing with accidentally engaging the electric resistance elements. It's also a very well deployed platform, so it could solve some of the API issues that James was talking about. And we need to do testing to find out. Finally, there's more system design that we can look at. Maybe there are other ventilation solutions that perform better than ducting. Maybe we can combine these with drain water heat recovery to reduce the load and therefore reduce electric resistance element use. And we need to support the industry with a design guide telling them how to do this well when they start doing it. Here's our contact information, but I see we're out of time.
Yeah, thanks, Peter. That's a great place to leave it. We're going to go ahead and switch gears now from small clustered heat pump water heaters in multifamily buildings to large central systems. And to do that, I get to introduce Jonathan Heller, and he's going to present on technology transformation in multifamily and commercial heat pump water heater systems. Yeah.
Thanks, Ben. Okay, jumping right to it. What I'm going to want to talk about is how we are transforming the market to commercial heat pump water heaters, and talk about the three pillars of that: developing the products, aligning policies, and educating the world about how to use these systems. So for those that don't know who Ecotope is, we're a mission-driven company that we have a research arm that's looking at emerging technologies, and we have a mechanical engineering arm that is working for architects and developers and delivering full mechanical engineering services to buildings. And we organize our business around 3 primary responses to the climate crisis that are relevant to heat pump water heaters. First, we have to stop burning fossil fuels in the buildings and move to heat pumps. The primary thing that has always been the focus of Ecotope's work is we have to do this energy efficient as energy efficiently as possible. We use the terminology design for off for our design team, with the recognition that the most efficient mechanical system is the one that you can turn off, and use of passive systems. And then finally, recognizing that as the grid transitions to reliance on solar and wind, when we use energy starts to matter as much as how much energy we're using. So Ecotope has been leading the commercial working group of the Advanced Water Heating Initiative, and this really brings together those 3 responses to the climate crisis that I was talking about before: electrification to heat pumps, focus on energy efficiency, and the load shifting that we can do with these large commercial systems. And we're envisioning with the Advanced Water Heating Initiative that we transform the market so that heat pumps are the primary way that is used to heat water in the country. And to do that, there's 3 areas of that we need to focus on. We need the products to be available to the marketplace. We need the policies aligned with those products, and then we need a market that knows about these products and is demanding them. And rather than do it in that order, which is often the case with emerging technologies, we want to do these 3 things simultaneously, because we are trying to have substantial transformation of the market within 5 years. So the target markets, multifamily is by far and away the largest user of hot water in the commercial sector. But with those grocery, lodging, and restaurant, those 4 building types represent about 80% of all of the hot water in the commercial sector. So first, what is a commercial heat pump water heater system? We want to get people to think about these systems in the same way that we think about a residential heat pump water heater. It has all of the same components that come in an integrated heat pump water heater are existent in a commercial heat pump water heater system. The compressor you can see there on the left-hand side, large commercial heat pump water heater. We've got a controls package. We've got the storage shown there in multiple tanks. And then finally, we've got the backup electric emergency temperature maintenance heating system that we're showing here in this larger built-up system as a temperature maintenance loop tank with electric resistance backup in it. So when we talk about commercial heat pump water heater systems, keep in mind that we're talking about this entire system. So we have been working for about 12 years on product development, working directly with manufacturers to bring these products to market in a way that can scale. And the vision that we have for these products is that, again, heat pumps become standard practice for water heating. We're shooting for an average annual system COP of 3 or better for the overall system, delivering both hot water and temperature maintenance. We want to be shifting to low global warming potential refrigerants in the heat pumps over time. We want to deliver them to the market in a plug-and-play fashion, so that a plumber can call up a distributor and say, I've got a 100-unit apartment building, and I need a heat pump water heater system, and the distributor can say, great, you need 3 of these tanks and 4 of these compressors and this control system, and here's the schematic, how it all goes together, and call me when you're ready, and I'll send somebody out there to help you start it up. So fully supported supply chain. We want them affordable, we want them reliable, and we want them to all have the ability to load shift. So to accomplish this, the product supply chain is really the key aspect of this market that we need to focus on. These are the folks that are selling the products to the designers and the contractors. These are the people that are teaching the world about the new products, and get us to the point where we can have reduced risk, reduced cost, and yield reliable and repeatable results. So what we've been working on to shift this market is really where we started from is what you see on the left-hand side of the picture there, where if we were going to deliver a commercial heat pump water heater system to a large multifamily building, it was going to be a custom engineered solution. As the engineers at Ecotope, we were selecting the heat pumps from one manufacturer. We were selecting the tanks from another manufacturer. We were selecting the temperature maintenance system from another manufacturer. The controls package is often coming from another manufacturer, and we're designing how they all fit together, how they all work together in the field, and then hoping that the installers do it the way that we designed it and that it all works. We can make it work that way, but that is a very complex, very expensive, very risky method for delivering these products to the market. So what we've been working on is shifting the market to what we're calling a plug-and-play solution that I mentioned before, where the plumber can just call a single source and get everything that they need pre-designed. So where we've moved the system primarily is to the middle picture there, where not everything is being supplied by a single manufacturer, but oftentimes a distributor will have a heat pump and a line of tanks and controls and pumps, and be able to put that together as a single offering to the marketplace. And then where we see things developing and see a lot of promises on the far right-hand side with fully pre-assembled skids, where everything is coming from a single source, put together in a factory and delivered to the site, ready for electricity and water connection, and it's ready to go. The process we've used to move these products in that direction is what we call the technology innovation model, where we start out engaging with the manufacturer first with a feasibility study to look at just the heat pump product itself and what part of the market it might best serve. And then working with them to pull together all of the parts and pieces needed for that full system and mock it up either in their factory or in a lab and do the applications testing so that we can see that all those products work together. Only then do we go out to real world demonstration projects and install measurement and verification monitoring equipment, get learnings about how well that system is working, what might need to be improved, and repeat that cycle until we have a product that we can really go to market with and begin training the market and the supply chain on how to deliver that. So one of our big victories as far using this model is the case study here for the Bayview Tower in downtown Seattle, 100-unit apartment building, existing building. And we worked with Mitsubishi for about 2 years to develop their heat pump product. And what you see there is a full system being delivered in downtown Seattle and then lifted up onto the roof of the meter shed there to serve that high-rise apartment building. So we worked with Mitsubishi on developing the system design, and then we worked with an outfit out of North Dakota called Steffes to pre-manufacture it into a skid product that could be brought and stuck on the roof. We were able to do this in an occupied building with only about 4 hours required to shift the existing water heating system over to this, and we reused many of the existing electric hot water tanks to provide the temperature maintenance. I don't have time to show you this, but towards the end of my presentation, there's a QR code that you can take a picture of, and it'll lead you to this case study that includes a virtual tour through the system, interviews with the mechanical engineer who designed it, with Seattle City Light, and you can kind of step through the whole system and see how it was put together and why and how it works. So I encourage you to take a look at this tour. The next thing we're going to be working on at the Bayview Tower project is to look at to test and demonstrate and document and optimize the load shifting capabilities of that system. So really trying to shift the operation of the heat pump to those low load periods to move them off of the peak hot water demand periods, which align typically with peak utility periods as well. So we'll be doing that work this year with funding primarily from Bonneville Power Administration. So at the same time that we're working with the manufacturers to develop the products, we're trying to put into place and align the policies, codes, and programs that will support the utility industry to support these products and support code development. The centerpiece of that is really the Advanced Water Heating Specification from Northwest Energy Efficiency Alliance, where we've added a commercial section to their existing Advanced Water Heating Specification. This is to really standardize that view of the heat pump water heaters as a system. So there will be a qualified products list developed for this specification that requires the manufacturers to submit not just their heat pump and the performance map for how that heat pump functions, but also submit the schematic for how it goes together with the storage and the temperature maintenance system and the sequence of operations, so that the whole system can be modeled, and we can develop a predicted system COP for each different product in different configurations in different climate zones around the country, and have a predicted system COP along with each product that's on that qualified products list. And we're using the EcoSim model, which we've developed using very similar model to what's being used within the California Title 24 software for modeling of these systems. And then over the next few years, what we want to see is installations submitting annual performance data through a national database that PNNL is developing, so that we can validate that the predicted system COP is actually delivered in the field. And if not, providing feedback either to the manufacturer, to the training for the installers, or to the modeling software to improve the ability of that software to predict actual results. Another key tool that we've developed over the last couple of years to support the industry is the EcoSizer program, which is really shifting the focus for designers on sizing these systems from a reliance on high capacity and low storage volume, which is typical for gas system, to much more reliance on a high storage volume and enough heat pump capacity so that the heat pumps are running between 12 and 16 or 18 hours per day as the most economical way to provide these systems, as well as the way that will allow for the most load shift capability. And we've seen the codes are moving at the same time that these products are being developed, that the spec is being developed, with a lot of pressure beginning to build on the code side to drive this market transformation as well. In California and the Pacific Northwest specifically, but also with a lot of other codes that are rolling out on the East Coast as well. Am I running out of time, Ben? I hear somebody breathing in the background.
Oh yeah, sorry. Maybe we should wrap it up in the next 2 minutes.
Okay, will do. Then the final pillar of that work is market knowledge and training the market. And here's the snapshot that will take you to a site that is currently being sponsored by San Diego Gas and Electric, and will provide access to, I believe we have 4 of these virtual tours with different types of systems in different configurations in multifamily buildings. And there's really a wealth of information that's been collected there. So I encourage everybody to take a look at that. And finally, yeah, this is my wrap-up slide. Just that Ecotope has kind of been involved in all of these different aspects, trying to make all of these things happen in parallel paths, so that within 5 years we can really have a significant impact on transition of the marketplace. Thanks for listening, and I'll answer questions in the Zoom chat.
Yeah, thanks, John. That was a super excellent talk. That was a really great overview of kind of what the possibilities are and where we are in the market. And next, we're going to move on to Nick Young from AEA, and he's going to give us what I think is a pretty detailed walkthrough on a large capacity CO2 heat pump water heater system and lessons learned from the field. So go ahead, take it away, Nick.
All right, great. Can you see my screen okay?
Can see you.
Sorry.
Yep, you're good.
All right, we're good. We're on. Okay, cool. Hi, everybody. My name is Nick Young. I'm Associate Director of Projects with the Association for Energy Affordability. I'm out of our California office. And yeah, I'm going to be talking to you all about large capacity CO2 heat pump water heating and some lessons we're learning currently, like as you know, today, yesterday, tomorrow from the field. And this is going to sound a little familiar from what John was talking about, because it's that same Mitsubishi product. So let's go through some of the basics for this project. So this is what I'm going to be talking about. It's an early launch demonstration, or a set of early launch demonstration installs of the Mitsubishi Heat 2.0. It was called the QAHV before being brought to the US, but they've rebranded it as the Heat 2.0. So that's how you'll see it referred to in the United States. It's a large capacity, low GWP CO2 heat pump water heater product. And we're also going to be doing extensive post-install monitoring and testing. So the R&D funds for this project and for these installs is coming from the California Energy Commission, Electric Power Investment Charge EPIC grant. And I believe that's actually Electric Program Investment Charge, and as well as program funds. So these installs are all in existing buildings, and the installs are being supplemented by a number of programs, including the Low-Income Weatherization Program for large multifamily buildings, the South Coast AQMD Multifamily Affordable Housing Electrification Program, or MAHAP, the LADWP Comprehensive Affordable Multifamily Retrofit Program, or CAMR, and the SoCal Regional Energy Network, or SoCal REN. So sort of our specialty is finding projects and stacking a million different funding sources to actually make these projects happen, and this is really no different. The team for this project, AEA is the grant prime. We are working on site recruitment and also overall project management for all of these demo sites, as well as data collection and analysis on the back end. Ecotope, John and his team are our engineering leads, but On some projects, they're the engineer of record, and on others, there may be an MEP engineer for that project, and so Ecotope just provides design review on those. We're partnered directly with Mitsubishi Electric Train US. They're the equipment manufacturer for the equipment, and as we've also got NBI and EPRI on the team heading up market transformation. So let's look in a little bit more detail at the actual equipment. So this is the Mitsubishi Heat 2.0. I've got the model number. It uses three-phase 208, 230 power. It's got a capacity of 136,480 BTUs per hour, or about 40 kW of output. COP, an AHRI rated COP of 4.11. You can see power input. I'm not going to read through all of these things, but this just gives you a basic idea of the parameters for this piece of equipment, and crucially dimensions. It's about 48 inches. It's about 4 feet wide, about 2.5 feet deep, and a little over 6 feet tall. So it's about the size of a VRF outdoor unit. And there are some additional components, and we'll talk about sort of what those are and what you need to keep in mind for those. So this product has a lot of advantages. First of all, low GWP. You really can't beat CO2 for GWP. And CO2 also has really great low ambient performance. Really the best of any refrigerant being used in current heat pump water heaters out there. It maintains output and efficiency well below freezing. So you can see in the chart in the upper right, you've got full heating capacity even at 36 degrees Fahrenheit or 2 degrees Celsius. And you maintain 50% of your heating capacity all the way down to minus 13 degrees Fahrenheit. So really fantastic low ambient performance out of this unit, which basically makes it a no-brainer in California, especially coastal California, where like we're barely even going to hit freezing. Also reduced electrical burden, in part because of its efficiency at optimal conditions, and that low ambient performance means you don't need to oversize your heat pump plant or your electric resistance backup to ensure hot water delivery for winter design conditions. So for example, if you had a design temperature of 36 degrees for your plant, well, the Heat 2.0 is not going to lose any of its capacity at 36 degrees Fahrenheit. And so you know that the nominal rated capacity is going to be your capacity at design conditions. Whereas, some other traditional refrigerant products, their capacity might be cut in half or worse as you approach freezing. And so if you wanted to maintain heat pump operation at those design conditions, you'd end up having twice as many heat pumps that are not going to be as efficient. So it sort of ends up ballooning your electrical requirements for your project. The Heat 2.0 units are also really quiet compared to some of the other large capacity central heat pump water heating products on the market. They're rated at 50. I see some cut sheets saying 56 decibels, others saying 60. Either way, that's the lowest number I've seen for a unit of this capacity. Other non-CO2 units are anywhere from 65 to 80 dBA, which can be pretty loud. And on the right, I've just got a illustration. This is from Mitsubishi of their twisted spiral gas cooler that they use for their heat exchanger between the CO2 and the water inside of the unit. So let's talk about some of our demo sites and the plant information for those sites. So we have 5 sites for this grant. The sites are in San Francisco, San Jose, Orange County, Riverside, and San Diego. I apologize. I had thought I had put the number of apartments or bedrooms served for each of these plants on this slide, but I don't have that. I can follow up if folks have questions about any of these. But there's a variety of building sizes, and crucially, there's a variety of sort of plant configurations. So you can see we have a number of sites with 2 heat pumps. Most of the sites have 2 heat pumps in the design, 2 of these QAHVs or Heat 2.0s. And the storage volume for these ranges anywhere from 360 gallons on the low side all the way up to 800 gallons on the high side. And part of the intention with this grant is not just to determine what is the absolute best, most perfect and optimal way to install these. Like we largely know what that is at this point. Large storage tanks, enough heat pump, like John said, to run the heat pumps for 16 to 18 hours a day to be able to recharge that storage. But in existing buildings, and we've got a lot of existing buildings that we need to retrofit over the next, not very long, you may not have space for that really large storage tank. So sort of what are the trade-offs, and like how little storage could you reasonably have and still have a relatively efficient system? Or how many more heat pumps would you need to make up for that small storage? And how would that system respond to demand events? And could you still do load shifting if you had enough heat pumps but not too much storage, and things like that? We had some site-specific hurdles for each of these in San Francisco. Even with the very low sound output of the Heat 2.0 units, we are running into some issues with the local sound ordinances because it's a very tight site and the heat pump units are going very close to an adjacent property. Um, we also are having to reuse the existing tanks. Or maybe we're not reusing the existing tanks, but the space is so small. They had, I think, 320-gallon tanks, and that's all they can use. So we're not getting like one large tank. We have three relatively small tanks because it's a small, tight, 100-year-old building, and that's all they can get into the space because I have to take these tanks like in through the front door, down around some stairs, and down into this tiny boiler room, and that's all they can get in there. Our project in San Jose, originally we were dealing with switching from the original 380 volt unit that was coming from overseas to the 208 volt unit that was UL rated, that Mitsubishi sort of eventually had. They were also switching from another manufacturer. So they were switching from I believe an R134A unit that had horizontal air discharge, and this one has vertical air discharge. So where you put it is different, and that sort of has thrown some things for a loop on the project. Our other projects have faced issues with electrical capacity. That's why our Orange County project has such a high ratio of storage to heat pump, because they're really limited on the electrical capacity side. That, a standard design really would have had 4 heat pumps for that project, but they were only able to fit 3 within the electrical constraints of the project. And the owner is getting some 11th hour cold feet, so that's also sort of thrown a wrench in the project. Um, Other issues we faced include electrical circuit runs, heat pump location, garage height. If we're trying to put it in a garage, do we have the headroom to do that? And these are all existing buildings, and every existing building is gonna provide a unique set of challenges for your install. So let's look at the general plant schematic for a Heat 2.0 plant. So what you'll have is on the on the left side, we've got our actual Heat 2.0 unit here. This is the heat pump unit, and it's going to live outside. And then inside, you've got 2 water pipes running from outside to inside to your secondary heat exchanger and this secondary pump. So what happens is the Heat 2.0 actually is looking at the tank. It's sensing tank temperatures. It doesn't show those sensors on here, but there are generally at least 3 sensors inside the tanks. It's looking at that tank temperature, and then it's turning on. And then this secondary pump is looking at the primary side, and when it sees flow, it then turns on the secondary side to then move water through that heat exchanger. Charge the tanks from top to bottom, just like any single pass. At this point, I'm going to assume folks here are familiar with a single pass heat pump water heater and not explain sort of in great detail what that means. It's connected to a swing tank into the mixing valve, just like sort of is becoming standard practice for central heat pump water heating systems. So that's the basics of sort of the Mitsubishi schematic, and this is actually an image provided by Mitsubishi in their marketing documents for the product that have sort of recently been finalized and are available. And this is an example plumbing drawing. So this is from our San Francisco site, and this was actually done by Ecotope. And so what I'm going to do is just call out some of the different components. So here we have the Heat 2.0 units here on the right-hand side. So everything's sort of reversed from what we were just looking at. Heat 2.0 units, in this case, there are 2 there outside. Then we've got our secondary pumps and heat exchangers there. We also have our primary storage tanks. In this case, we have 3 that are in series. And then finally, we have our recirc pump, our swing tank, and our mixing valve. One thing you may notice is that on our recirc return here, in addition to going into the swing tank, we also have a manifold here to send the recirc return back to the primary storage tanks. And one thing we're doing with this project at a few demonstration sites is actually testing the viability or feasibility of returning the recirc return to the main storage tanks. I know that's sort of forbidden to do in heat pump water heating systems. But we're interested in studying the potential impacts of that on this system, because we have seen it done in some actual systems in the field. And if you can do it in a particular way, it may work. And we're trying to test that and see what the impacts of that really are. So some challenges we're facing and things we're learning currently. First is that everyone is learning as we go, not just our team. So this product is new to us, but it's also new to the Manufacturers USA team. The purpose of this study is actually to help work out the kinks for bringing the Mitsubishi Heat 2.0 to the US market. So we've had quite a large number of corrections. Luckily, we've had Ecotope on the team, so as they learn things from Bayview, they can convey that to all the projects going through this R&D project. But that always ends up having you end up having a lot of coordination, a lot of changes, and it's great to get those learnings. But conveying them and getting everything coordinated can be very challenging. After these initial demo sites, we really think a package system from Mitsubishi Train will be standardized and easy to order. That's the intent. And these demo sites are really to try to help work out what exactly that standardized package system will be. Another challenge we faced is that these are infill sites and they're very tight. Sound levels at neighboring properties can be a challenge. And like I showed earlier, tank size, you can be limited on tank size. For example, this building that we're looking at here in this image, with everybody trying to figure out what's going on, that picture was taken last week. We've got the plumbing foreman on the right. Next to him is the plumbing engineer. And then the two other people on the far left and in the background are both from Mitsubishi's startup team. This building normally would only have needed, really, per the plumbing engineer, would only have needed one of these Heat 2.0 units. But because they were so limited on storage, he chose to specify two. Also, so they have some redundancy because it's a new product for them and for the owner. Other challenges and things we're learning. So this product requires a secondary heat exchanger and pump. It's required on the Mitsubishi Heat 2.0. Unlike most R134A and smaller CO2 systems like the Eco 2, those don't require a secondary heat exchanger. This one does. The current spec is a SWEP 2-pass heat exchanger. It's relatively compact, and SWEP does offer an insulated shell, but you do need to specify that if you want to get it. Also, we've learned sort of through Ecotope's experience on Bayview that you really need to have a minimum volume on the primary side of 10 gallons. And so with a 3/4 inch pipe run between the heat pump and the heat exchanger, you'd need about 50 feet of pipe. I think both ways. So what can you do to get that volume? Well, you could have larger piping, but piping tends to be very expensive. So what we're seeing is projects are going with either a flow-through expansion tank that's then insulated, or a couple of projects have found a real MacGyver solution, which is a small electric water heater with the element removed or just not connected, because you have a small 10-gallon fully insulated component that's easy to purchase and relatively cheap that can get you that volume on the primary side. Other challenges that we're facing, operations modes and controls. The modes are programmed by Mitsubishi and their startup technicians into the unit. There is an external control module that can tell the unit when to enter each mode. But are those always arriving at the site at the same time as the heat pump? Not always, right? This is sort of all getting worked out as we go. The product can be started and operated without the external module, but Mitsubishi is going to require the control module for all units going forward. Other challenges have just been the distribution channels, as this is a new product. Local reps early on may not have a great handle on the product until they've been selling it for a while. This is the case sort of for all products. Anytime there's a new product, it takes a while for the reps to learn sort of what it is and how it works and what all the things are. Supply chain processes are being worked out. They're working through packaging, controls, and distribution. And we're working through those as the manufacturer has been figuring it out, right? And these early demonstrations are challenging, and they still are. We're not done with them. But working with a responsive and invested manufacturer like Mitsubishi can make them doable, and that's really what we're seeing. And I'll just say that once the specifics of the packages are ironed out, local reps are trained, and supply chains are standardized, which is happening very rapidly, this Heat 2.0 is going to be a very competitive offering that should be pretty easy to specify for really any type of project. So we're excited to continue working on this project, and yeah, we'll be excited to share learnings and data we've collected from these installs maybe at next year's Hot Water Forum. Thanks so much.
Great, thank you, Nick. Another great presentation. I'd like to thank briefly all 4 of our speakers. And if you have questions, please join us in the Zoom chat. The link is over on the right side of your screen with the passcode. So we'll see all of you over there shortly.